I welcome you this NPTEL lecture on earthquake resistant design of foundations. And today we are going to discuss 39th lectures, which is foundation on slopes. And as we discussed in the last lecture, that is 38th lecture, that this lecture is part of the last module of the course, that is miscellaneous. Under this module, we have two sections. One is rock foundations, where some numerical examples was discussed, and the second on cellular foundation on slopes. And we are going to talk today the cellular foundations on slopes, the second part. What we have covered so far when we discussed that in the last lecture on foundation on slopes, we discussed background, static bearing capacity. Now we are going to extend the same thing for seismic bearing capacity, codal provisions, and some numerical examples. So let's talk first seismic bearing capacity. When we talk about seismic bearing capacity, we are going to talk from two researchers who have worked, and we are going to discuss some of the results presented by them. One is by Kumar and Rob, 2033, and another is Chakrabarti and Kumar, 2015. So here Kumar is this author, Professor Jayant Kumar at IIC Bangalore, who have done nice work in this area. And his work and his research teams. So this work is coming from there, and we are so this is acknowledged. And what I'm going to present is from the results taken from these papers. So what is here? What the Kumar and Rao in 2003 studied the bearing capacity of footing on the slopes. And what they have found that an increase in the magnitude of alpha s, that is basically alpha h is nothing but here the horizontal seismic coefficients, brings an appreciable reduction in all the bearing capacity factors, and the magnitude of the bearing capacity factors decreases further with increase in down inclination. So there are two issues now here when we discuss with the bearing capacity. One thing, the slope, which was coming even when we consider the static bearing capacity, the effect of slope was discussed earlier also. So the effect of beta, which is the slope angle, has been discussed earlier too. But the effect of alpha h was we are discussing now first time. So let's discuss the first effect beta again, review it. These charts are for NC. And these are three different charts for this NC. NC, you know, NC is the bearing capacity, dimensionless bearing capacity factor in Tarjagi's equation. So in this case, the value of NC, which is ranging from here, 0 to 6, and this is logarithmic scale, you could see here. So this first chart is for phi equal to 0, second is phi equal to 10 degree, and then 20 degree. Naturally, when the phi increases, first of all, for all other parameters keeping constant, the value of NC is going to increase, number one. Second thing, when the slope angle increases from 0 to 50 degree with an increment of 5 degree, 10 degree like this here, then you could see for a given value of alpha h, or let's say for a static case alpha h is 0, then still that due to the increasing slope angle, the value of this bearing capacity factor will decrease. Okay? Now on the top of it, for a given value, for a given slope angle, let's say beta equal to 0 degree, or even beta equal to last 50 degree. So you could see that when you increase the value of alpha h, then there is a quite much reduction in the bearing capacity, and this is happening for other values of phi also. And this bearing capacity factor decreases significantly as the value of horizontal seismic coefficient is increasing. So and it is expected that during the earthquake, the bearing capacity of foundation decreases. Number one, even this will decrease for a given, let's say when beta can be equal to 0, that means there is no slope, or slope angle is 0, that still the bearing capacity will decrease due to increase in seismic coefficient. So this is for NC. Similarly, Kumar and Rao have one. The variation for NQ also, that is the second factor. And when the NQ is given here, 4 charts are there for 10 degree, 20 degree, 30 degree, 40 degree. One thing is here that in this case, these charts are for a value less than 5. That means it is assumed here that the value for this case, that the value of the beta should be less than 5. So in this case, what is assumed that beta should be less than 5. All the charts get terminated in this case for, let's say, for 5 to 10 degree, it is up to 5 degree. For 5 to 20 degree, it is up to 15 and 30, and so on. So you could see that. Now, within that, beta equal to 0 degree means there is no slope. When alpha h increase, NQ decrease, and it becomes almost very negligible. So you could see at that for all values, when the alpha h increases, this is terminal. And this is the case when these charts are getting terminated. That means after that there is a issue related to instability. So that means for when you have very high, let's say the slope angle for 35 degree, then you cannot keep the value of alpha h more than 0.1. So that is a that's limiting point. So same thing is, let's say, for when beta equal to 10 degree, then in this case or this case, 5 equal to, you can go up to 0.4. So that means to increase the seismic coefficient, you require that your phi value should be sufficient. If your phi is less, then you cannot go beyond, let's say, certain value of seismic coefficients. Same thing is for another n gamma, similar kind of variation for 4 values of phi equal to 10, 20, 30, 40 is shown in this figure. But one more thing has been added here for n gamma, that for n gamma, which is related to the unit weight and the bearing capacity factors, there are two curves for a given value of beta. One is when you consider that this failure envelope is both sides of the footing, and this legend is on the single side. Naturally, when you consider the failure envelope from both sides of the footing, then your value of n gamma will decrease. So this single side, when you consider, it is higher value than this. So for conservative side, you will be using without this legend here. So other things are more or less same as we discussed in the last figure, that first of all the value of beta should be less than 5, and as well you increase the value of alpha h. As a result, when alpha h increases, there is a decrease in the value of n gamma. So this was the result by Kumar and Rao. So the Kumar and Rao have considered here that the effect due to alpha h on this. Now, whatever we have discussed earlier, once you find the modified bearing capacity factors, then you can use Tarjagi's standard bearing capacity expression, which is given here, Q equal to C and C plus Q plus half gamma, V and gamma. So this is the standard equation which we are using from a long time for shallow formation. And NC, NQ, and N gamma should be determined for a particular value of alpha h and particular value of beta for different values of phi and beta, and that should be taken from previous figures. And as a result, you can determine the value. So naturally, when NC, NQ, and N gamma decreases, whatever value you get QU from this equation will be less. So there is a reduction. So this was the results presented by Kumar and Rob. Now continue with that. Another work was done by Chakraborty and Kumar in 2015, and this was earlier factors, given seismic factors for flow and slope using the method of stress characteristics. Now this is in 2003. Whatever we have discussed was based on method of stress characteristics, but Chakraborty and Kumar used the lower bound theorem for the limit analysis. And what is done in lower bound theorem of limit analysis? The collapse loads is expressed in terms of the bearing capacity factor. Now, instead of 3 bearing capacity parameters, the Chakraborty and Kumar, they have used only 2. One is NC, and NQ and N gamma is clubbed in N gamma Q, and now bearing capacity will be found from this expression. So continue with that. So what you have, let me change it pointer and arrow here. So what you have, this is the variation of NC with KH and beta. First of all, Chakraborty and Kumar use the, instead of alpha h, they have used KH. But this is the same thing. Alpha h and KH are same, where KH is horizontal seismic coefficient and alpha h was also horizontal seismic coefficient. And the value has been from 0 to 0.5, 0.1, 0.2, 0.4, 0.5. And these charts are for 4 values of phi, which is 10 degree, 20 degree, then 30 degree, and 40 degree. So you have A, B, C, D, 4 charts are there. So what you have, all the charts are for D by B equal to 1. That means the depth of footing is same as the width of footing. Now you can see these charts are again for beta equal to 0 to 50 degree. These curves are there. And the values calculated are shown on these results. One can see easily that for a given value of beta, as the KH increases, there is at the same time there is a decrease in the value of NC. And when the NC decreases and when beta increases, and this was a particular value of beta. On another side, when the value of beta decreases, let's say increasing, the top one is for beta equal to 0 degree, and the bottom one is for beta equal to 50 degree. So what you have from 0 to 50, as the beta increases, then there is a reduction in NC. So naturally, as we discussed earlier for the static case also, that due to the reduction in the increase in the beta value, the value of NC decrease, number one. Number two, that NC also decrease when the value of KH decreases. So this result is similar, but the trend is similar to what we have observed, but this is based on lower bound theorem, and naturally the values are different. So the trend of the results are same. So this was the case for NC. Now going to this N gamma Q, which is again, this curve is for 10 degrees, so it is up to 5 degree only, and so on. This is for 10 degree, 20 degree, 30 and 40. So you could see the trend is still same as seen observed earlier, and with the here all the it is on the log scale. So N gamma Q values are varying with beta and KH. So when the beta increases, this decreases as well as with the KH. So this was by Chakraborty. Now let's discuss what is the provision given for IS codes by the Codal provisions. We are going to discuss 2 Codal provisions. One is from Indian Standard Code 1904, published in 1986, and Eurocode 8 Part 5, which is published in 1998. So what this says about for the design of foundation on the slopes. So let's discuss first Indian Standard Code. So Indian Standard Codes put some limitations that when you design your footings for the slopes or on the hilly areas, then in that case some restrictions are there. And what is said here, that the depth of the footing shall be such that the difference in footing elevations shall be subjected to the following limitations. And what are the limitations? First, when the ground surface slopes downward adjacent to a footing, the sloping surface shall not intersect a frustum of bearing material under the footing having sides which make an angle of 30 degrees with the horizontal soil. So you could see in this figure, it is, let's say this is footing, single footing on the slope, and this is the lower edge. If I draw a line at an angle 30 degrees with the horizontal here, and then this line should not match, should not cross the slope. That means this either one way, that they should be parallel to each other or they should be diverging. They should not be converging. That means they should be going away from each other. They should not be coming towards each other. So this is the condition. That means this is the location of the footing should be such that this line doesn't cross each other. The second thing, the horizontal distance from the lower edge of the footing to the sloping surface, that is this distance, should be at least 60 centimeters, 600 mm for the rocky side, or 900 mm for the soil sides. So if you are not sure whether it is soil and rock, so try to keep it at least 900 mm, 90 centimeter, which is about 3 feet from the slope to the lower edge of the footing. So this is the first condition prescribed by Indian Standard Code. The second one, if you have a number of footings, if you have 2 footings, and in that case, this requirement are different for granular soils and clay soils. In case of granular soils, a line drawn between the lower adjacent edges which shall not have a steeper slope than 1 vertical to 2 horizontal. So you have like you have here this line which is adding the 2 lower edges of the footing then this slope should not be more than 1 to 2. But in case of clay, then you will connect this lower edge and the upper edge. Then it is expected that this slope, which is lower expected than this one, earlier one, but still its value should not be one vertical, should not be more than 1 vertical to 2 horizontal. So this line, black line, is for granular soils, while the red line is for clay soils. So this is a requirement when you have 2 footings on the slopes, adjacent footings, which are at different level. This is at one level and another. Continue with this. Now there are landslip areas also in the hilly areas, and this Indian Institute of Codes prescribes some that guidelines. And what are those? The construction of a structure on slope which are suspected of being unstable and are subject to landslip shall be avoided. Number 1. On sloping ground on clay soils, there is always a tendency for the upper layers of soil to move downhill, depending on type of the angle of slope, climatic conditions. In some cases, the uneven surface on the virgin ground will indicate that the area is subjected to small landslip. Therefore, if used for foundation, will obviously necessitate special design consideration. So, the clay require more treatment than the granular soils, particularly on the sloping ground. The third one, where there may be creep of the surface layer of the soil, creeping effect, protection and speed may be obtained by following special design consideration. What are the on sloping sides? Straight foundations shall be on a horizontal bearing and step. At all changes of levels where there is a change in the level, they shall be left at the step for a distance at least equal to the thickness of the foundation or twice the height of the step. So whichever is greater. Here, the step shall not be of greater height than the thickness of the foundation. So step height will be less, foundation thickness will be more, but the requirement of lapping that at least thickness of the foundation or twice the height of the step, whichever is greater. Then the next requirement is, if you are cutting and excavating or sloping ground near and below foundation level may increase the possibility of shear failure of the soil. So cutting, excavation, they will increase of chances the shear failure. And in this case, the foundation shall be well beyond the zone of such shear failure. Next, if the probable failure surface intersect a retaining wall or other structure, the latter shall be made strong enough to resist any unbalanced thrust. In case of doubt to the stability of the natural slopes or cutting, the structure shall be kept well away from the top of the slopes, or the slope shall be established. Then next, cutting and excavations adjoining foundation reduce stability and increase the likelihood of differential settlement. Their effect should be investigated not only when they exist, but also when there is possibility that they are made subsequently. Where a structure to be placed on sloping ground, additional complications are introduced, and the ground itself, particularly if of clay, may be subjected to creep or other forms of instability, which may be enhanced in the same direction the ground surface. If the slope of the ground is large, the overall stability of the slope and substructure may be affected, and these aspects should be carefully investigated. All these issues have been already given in IS code 1904. So if you have a copy of that, you can go through that, or otherwise you go from here. Now these slides was related to the IS Indian Institute Code 1904. Eurocode 8, Part 5, which is published in 1998, also put some requirement. General expression is that the stability against seismic bearing capacity failure of a cell of stood footing resting on the surface of homogeneous soil may be checked by relating the soil strength, the design action effect at the foundation level, and the inertia forces in the soil. For purely cohesive soil, if what are the requirement, particularly if you want to have this what is called the ultimate bearing capacity. So that is for purely cohesive soil or saturated cohesiveness soil, the ultimate bearing capacity under a vertical concentric load, which is denoted Nmax. Nmax is here typically load, N is looks like a number, but Nmax is denoting here vertical bearing capacity. And this can be found from this relation, but this will be applicable for cohesive soil. Pi plus 2 C bar divided by gamma M into B. Where C bar? This is C bar actually. So this is C bar. Where C bar is the underhead shear strength of soil. So which could be only Cu for cohesive soil, or the cyclic underhead shear strength tau Cy U for cohesionless soil. and gamma m is the partial factor for material properties, and B is the width of the protein. So gamma m will not have any unit. So the unit of Nmax will be C bar into B, which is basically force per unit length or kilonewton per meter. So this will give you ultimate load for per unit length. Now this was the case for positive soils. The Eurocode suggests for purely cohesion-less soils, that is granular soils, when you consider dry cohesion-less soils or for saturated form without significant pore pressure building. If you have dry, fine. If you have saturated, then there should not be built up of pore pressure. The ultimate bearing capacity of foundation under a vertical concentrated load Nmax is given by this relation, where half into rho c, where rho is mass density, g is the expression due to gravity, 1 plus minus AV by g, v square into n gamma, where AV is the vertical ground acceleration due to seismic excitation, and B is the width of the foundation, and gamma is the bearing capacity factor, which is a function of the design angle of the shearing resistance of soil, that is phi dash. So this was about some of the things which is prescribed by Eurocode. Now let's discuss some numerical examples. We are going to talk about two numerical examples. One is for saturated clay, another is for granular soil. And these examples are for static case. Yeah, of course, it can be extended for seismic case also. So the first example is in this question, which is shown a continuous foundation on the top of a saturated clay slope. So what you have here, this is foundation, and this foundation is not on the face of the slope, rather it is on the top of slope. And what is asked, estimate the ultimate bearing capacity by Maheshwari's method and Hansen and Basics method. So first, let's say using Maheshwari's method. In the first case, Maheshwari's method's ultimate, because it is said here, it is saturated clay. So that means only the first term C and CQ will be applicable, because others N gamma and NQ will be 0. So in this case, Maheshwari's case, N gamma Q will be 0. So as a result, Q is given, ultimate bearing capacity is simply given from this relation. Now, to find the value of NCQ, we need to use the chart which is given by Maheshwari, and we need to have some parameters. First of all, for the given data, df by b, you could see df is 1.5, b is 1.5, so it is simply 1. b by b, b is the distance from this angle to the face of the footing, which is 0. So b by b is 0. And since height of the slope is 7 meter, while width is 1.5 meter, h by b is greater than 1. So we can use that stability number ns equal to 0. So let's use the chart for Maheshwari, which gives the value of NCQ for a given value of phi, and phi is given 0 here. Sorry, for given value of NCQ for given value of the angle of slope. So this is here. So here what you could see, that NCQ is given here, while on the x-axis you have b by b or b by h, because ns is 0, so b by b is already 0. So we need to use this when b by b equal to 0. And from this chart, you need to pick up a line for df by b equal to 1, and phi is given, sorry. So here df by b equal to 1, b by b equal to 0, and ns equal to 0. So with this, what you have? So because beta is given 30 degree, beta is slope angle, which is given to you 30 degree. So when beta is given 30 degree, the dotted lines is for df by b equal to 1. This is the line here. And for this line, we pick up 30 degree and df by b equal to 1. So we will be using this line, but when b by b equal to 0, then this line gives you the value here about 6.5. So 6.5 is the value of NC from this NCQ, and 49 is given to you C, value of C, 49 kilopascal. So simply when you multiply, then you get 318.5 kilonewton per meter square, or you can say this is basically kilopascal. Okay. Then going to this, if we use the Hansen and Basic method, then Hansen and Basic method, we already discussed in the theory that ultimate bearing capacity, this is the CNC part, this is gamma df and q, and this is gamma b and gamma. So this, when you combine, so when you put the numbers here, Hansen and Basic, but beta is given to you minus twice into beta. Beta should be in terms of radian, pi by 180 into 30 dB. The value of C is given 49, so sorry, this typing is somewhere. Then plus gamma D, gamma is 18.5, DF is 1.5 meter, and then beta is again 1030 degree. So this way, once you have, then you complete the second term. The last term is here minus gamma, B is 1.5, and sine beta, third sine 30, and 1 minus 10 beta is 1 minus 10 30 whole square. So when you put all the numbers and when you calculate, then you find the ultimate bearing capacity. In this case is 203 kilonewton per meter square. That is kilopascal. So in this example, this Mehrov is giving the higher value. The value obtained by Hansen and basic is quite low compared to that shown by Mehrov. It was 318. It was 203. That means the value shown by Hansen and basic is about 2/3. Or 2/3 of which is represented by Mehrov. Okay, so this was the case for the clay soil, saturated clay soil. Now let's discuss another example, which is for granular soil. And the problem is given here. So you could see what is the problem here. In this problem, the footing is given, width is 1.5 meter, and then the value of gamma is given 16.8, phi is 40 degree, and C equal to 0. So there is no cohesion. Earlier, phi was 0, C was present. Now C is 0 and phi is, and the angle is same as beta is 30 degree as before. Okay. So what you have from Mehrov's method, because C being 0, so there will be one term only, that QE will be given by half gamma B n gamma. To determine the value of n gamma Q, again the dimensionless parameters E by B is 1, dF by B equal also 1, because dF is given here, and phi equal to 40 degree and beta is given 30 degree. So we use the chart which is given here for phi equal to 40 and beta equal to 30 degree. So what you have in this chart, you see this is the chart given. So B by B equal to 1 first of all. Okay. Then dF and by B, that means we need to use the dotted line rather than solid line, dotted line. So we'll be using, and the value of beta is given 30 degree. But this chart is for either 0 degree beta, 20, 40, there is no for 30 degree in this case. So as a result, you have the value of 30 when phi is coming, let's say for beta equal to 30 degree and phi is 40. Okay, so your phi for 40 degree, the charts are here. So these are the charts. These all three lines are for basically phi equal to 40 degree. And we need to use the dotted line also, not solid line. This solid line is for phi equal to 40 degree. So 1, this is for beta equal to 0, this line is for beta equal to 20, and this is 40. So because there is no curve for beta equal to 30, so we pick up the value for 20 and 40, which is about 110, and this is about 70 here. So because it is on the log scale, you need to understand it is on the log scale. So 70 plus 110 divided by 2 will be the average value here, which is shown here. So this is the value of n gamma Q will be 180 divided by 90 multiplied by this factor. So you got 1134 kilonewton per meter square, that is kilopascal. Then you use the Mehrov's method. Now coming to Saran and Handa's method and using this dimensionless parameter. First of all, see that C equal to 0, so we don't require NC. We require NQ and N gamma in Saran and Handa's method, and the value of phi equal to 40 and beta equal to 30 degree. So we use this phi equal to 40 degree, that means first column, and beta is given 30. So beta is 30 here, okay, and this is the case when dF by B is also 1 and B by B equal to 1. So the value of N and this NC NQ and this N gamma is 131.34. Similarly, NQ for when B by dF by B equal to 1 and this 1 and this is 28.3. So we pick up from the tables which is given by Saran, Seat and Handa and use the equation for the bearing capacity, two terms. So this is the ultimate bearing capacity. But the second method is Q NQ plus half gamma B N gamma. And this is what you get B by B equal to 1 for these values. This values is already read out. And you put all the numbers here, Q, NQ, and half 16.8, which is gamma into V into N gamma. So you end up in the value 2368 kilonewton per meter square. 2000. That means the ultimate bearing capacity 2368 kilopascal. Now, last method, that is the stress characteristic solution. In case of a stress characteristic solution, the ultimate bearing capacity is simply given by half gamma B and gamma Q, where N gamma Q can be found from this chart. And this chart, we need to pick up a line for V by V equal to 1, that is the solid line, and phi equal to 40 degrees. So out of these two lines, you collect the solid line, and for beta equal to 30 degree, you read. So this comes somewhere beta equal to 30 degree, and this is the case here. So once you raise here, so you will come up somewhere. So this value is more than 100, and gamma Q is about 110. So once you put this number, then you get 1386 kilonewton per meter square, the ultimate bearing capacity. So if you compare free bearing capacity, it was 1134. Then you have 2368, 1386. That means the Marov solution is giving the least value in this case, and Saran and Handa is giving the almost double than the Marov, and the intermediate is given by this stress characteristic solution. So this is complete the numerical examples for both clay as well as granular soils, and these are some of the references which are used here. The Chakravarti and Kumar's paper in the International Journal of Geomechanics, book by Brajan Das from Cello Foundations, Eurocode, IS Code, and Kumar and Roorkee. And with that, I thank you very much for your kind attention.